Now we will be looking at another application of the third law, a case of a rope pulling a box. There is a contact force called tension that develops in the rope. For example, in this figure, you see a block pulled by a rope with a force F. There is a tension force T in the rope. So if we assume that the mass of the rope is 0, then this tension force is actually equal to the applied force. So in general, when the mass of the rope is not 0, or the rope is deforming, that is, the rope has its own acceleration, we cannot assume that T equals F. But for this course, we will always assume that the mass of the rope is 0 and the rope is not also deforming. So we can always assume that tension equals equal to F, equal to the applied force, basically, in this particular scenario. And so what is tension? Tension is basically a reaction to an applied force. When we are summing all the forces acting on a system of objects, we do not consider the tension forces. This is because tension is kind of an internal force between two objects. And if you are treating the collection of objects as a system, then you don't need to consider the internal forces. But if you are looking at one individual object inside the system, then you need to take the tension force into account. So let us look at a slightly more complicated system. So we have two masses here, M1 and M2, and they are tied together by a rope and pulled by a force to the right. So let us see what are the tension forces in this problem. So again, we will assume the mass of the rope is 0. So over here, what happens is that part of the applied force gets converted into tension forces between the two objects. So these are action and reaction forces, the T1 and T2. For example, M2 is pulling M1 with a tension force T1, and M1 is pulling M2 with a tension force T2. Because the mass of the rope is 0, this T1 and T2 are equal in magnitude, but as you can see, they are oppositely directed. That is, T1 equals minus T2. So if you treat the system as a whole, the collection of the two objects and the applied force, then the tension forces cancel each other, and you don't need to consider them when you are when you are obtaining all the forces that are acting on the system as a whole. But if you are considering the forces acting on M1 and M2 individually, then you need to consider these tension forces. So there will be many problems related to forces where you have to do free body diagrams and apply Newton's laws, all three laws, also action and reaction, the third law. So there are some problem solving hints that I would like to give you for those. So when you are analyzing a problem, it is always good to use vectors basically to represent forces. First, establish a coordinate system, and then make sure all your quantities are in the same units, the units are consistent. And then you have to figure out what are the appropriate equations to use. For example, if you are solving a force problem for which you need Newton's second law, you want to use F equals ma, or whether it's a third law, then you need to treat the two forces as equal and opposite. You have to select the appropriate equations for the problem. And then you have to figure out what is the problem asking about, what are the unknowns, and how you can solve them. And then when you have obtained a final answer, you want to make sure the answer makes sense. For that purpose, you can check with your free body diagram if everything is consistent. The magnitude of the forces you are getting, are they consistent with your magnitude and direction of the forces? Are they consistent with your free body diagrams? And also, if you are getting extreme values, then you want to make sure, do some sanity checks and make sure they are okay. Pulling forces, so we will go through a set of problems. It will be clear to you how to solve problems involving tensions. Over here, you see a similar system, two masses, M1 and M2. M1 is 4 kg and M2 is 6 kg, being pulled by a force F. And so there is a tension force T between in the ropes connecting these two objects. So we are told that the whole system is accelerating at a rate of like 2.5 meters per second square. And the problem asks us to find the magnitude of the force F. So now we can treat this as an entire system and solve for M. And if we sum all the forces acting on the system, then it is just the applied force F. We can ignore T in this case. And so we just apply Newton's second law, F equals ma, but we don't treat the individual masses, we take the mass of the system as a whole, which is 4 plus 6 kg, 10 kg. And we are given the acceleration, so we can easily find F. And it comes out to be 25 Newton here. Then the second part of the problem asks us to find the tension in the rope connecting the two boxes. And for this case, you have to, it's better to draw a free body diagram for the 4 kg mass. And in the free body diagram, if we ignore the vertical forces, because the vertical forces are not playing a role in this problem, we see that the only horizontal force acting on the 4 kg mass is the tension force. F is not directly acting on the 4 kg mass. It is just T alone that is acting. So the free body diagram just shows the tension force T on the object. Now we know the 4 kg mass is accelerating at 2.5 meter per second square. The whole system, both the 4 kg and the 6 kg masses, they are all traveling together at 2 meter per second square acceleration. So then we apply Newton's second law, F equals ma, to this mass alone, the 4 kg mass alone. And we see that we get a value of 10 Newton for this case. Now, let's look at another problem, slightly complicated, because now we will consider kinetic friction acting on these two objects. So again, we are told that the two masses both are accelerating at 2.5 meter per second square. So the problem asks us to find the tension in the rope connecting the two boxes. The problem tells us that we can assume the coefficient of kinetic friction to be 0.1. The best thing to do is to draw the free body diagram again, taking into account all the forces acting on the 4 kg mass. And this is what the free body diagram looks like. So now you have to consider the vertical forces. The frictional force acting on this block depends on the vertical forces. That is the normal force, right? We see that there are actually 4 forces acting on this block. The tension force pulling it to the right, the force of gravity, the weight of the block acting vertically downward, and the normal force, the reaction of the surface acting vertically upward, Fn, and then the frictional force, force of kinetic friction, that is opposing the motion of the block. So that means it's opposite to the tension force acting to the left. Now we can use Newton's second law along each of the axes. For the horizontal axis, we have T minus Fk1 equals ma. A is given. We know the mass of the block also. We need to find T. The problem tells us to find T, but we don't know the frictional force Fk1. But we have enough information to find this frictional force Fk1. So we know that Fk1, the force due to kinetic friction, is equal to the coefficient of kinetic friction times the normal force. So it is mu k times Fn. And since there is no vertical motion of the block, we know that the forces in those directions cancel out, and we see that there are only 2 forces, Fn and mg. So Fn minus mg should be equal to 0, which means the normal force is equal to the weight mg. And so then we can insert mg in place of Fn, and we see that the frictional force is actually mu k times mass of the block times the acceleration due to gravity. So the kinetic friction, the coefficient of kinetic friction is given in the problem as 0.1. The mass is given. We know the acceleration due to gravity. Now we know force due to kinetic friction, Fk1. So we know all other variables in the problem. So we can find the tension force T. Rearranging the equation, the tension force becomes ma plus mu k mg. And if you plug in the numbers that are given in the problem, you get something like 13.9 newtons. Now let us go to the second part of the problem. And the second part asks us to find the magnitude of the force F. Now we need to treat the two blocks as a system as a whole, right? And see all the forces that are acting on the system. So there are actually 3 forces acting on the entire system: the applied force F, the frictional force Fk1, and the frictional force Fk2 acting on the 2 objects. We can ignore the tension forces because they are action-reaction force pairs, and they are internal forces that cancel out when you are treating the system as a whole. So to find F, we need to find the two frictional forces Fk1 and Fk2. We have already found Fk1 in the first part of the problem, and similarly we can find Fk2 in the same manner when we apply the same technique on the 6 kg block, because Fk2 is just equal to mu k times the normal force Fn acting on the 6 kg block, and the normal force in that case is equal to the weight of the 6 kg block mg, and we find that the frictional force acting on the 6 kg block is actually 5.88 Newton when we plug in the numbers. And now if we write Newton's second law on the system, we have to sum all the forces. So F minus Fk1 minus Fk2, the frictional forces are opposing the applied force F, and that has to be equal to the total mass of the system times its acceleration. And now we know Fk1 and Fk2, the masses are given in the problem. The acceleration is also given to be 2.5 meter per second square. So if we plug in all the numbers, we get a value of 34.8 Newton for F. Okay, then let us look at another problem. This is a mass suspended from a spring, vertically suspended, and it's at a static position. There is no velocity v equal to 0. It's just static, stationary. So the problem asks us to find the total sum of the forces acting on the block. The block has a mass of 10 kg, and if we draw the free body diagram, we see that there is a tension force pulling this is the force that the spring is applying on the block. And then because the block is suspended vertically, its weight is also acting downwards. So the tension and the weight are acting in opposite directions. So the weight we can easily find because we are given the mass of the block and weight is just mg. So we write the force equation from Newton's second law. T minus W equals m times a, and since the block is stationary, acceleration is 0, and we see that the tension force is actually equal to the weight of the block mg. And if we plug in the numbers, 10 kg for mass and 9.8 meter per second square for g, we get 98 newtons. It's a simple problem. So let's look at another problem, a slightly more complicated, because there is an applied force in this case. It's given that F equals 10 Newton is acting on the block vertically. So you can also think of this as a spring force. But in this case, the system is not static because there is an applied force which may cause acceleration if it doesn't balance the other forces in the system. So, and the mass is again suspended vertically, so the weight is acting vertically downward. And in this case, we need to find the net force acting on the object. So the net force is just F minus W. We see that there are only two forces. And we don't need to consider the tension force in this case because the tension force is equal to the F. And we are actually evaluating the total forces acting on the system. So we don't need to consider the tension force. And we find that that this is just 10 Newton, the applied force, minus the weight, mg, which is 98 Newton, 10 times g, and it comes out to be minus 88 Newton. And the minus sign indicates that the net force is acting vertically downward, basically. So the applied force is not sufficient to cause an upward acceleration of the system. So another example here, slightly complicated. There are two masses now hanging together with a rope connecting the two masses and another rope connecting the first block to a surface, and the blocks are suspended vertically. So the first block is 5 kg and the last block is 10 kg. There are two tension forces acting on it, T1 and T2, because these are different segments of the rope. So we are asked to find out the values of the two tensions, T1 and T2. Now let us work on each body at a time. First, let us look at the 10 kg block and draw all the forces that are acting on it, the free body diagram. So you see that there are two forces, W2 acting vertically downward, this is the weight of the block, and the T2 tension force acting vertically upward. And because the system is static, the problem tells us that there is no velocity, so the system is static, so the acceleration is 0. So T2 minus W2 equals ma from Newton's second law, and this has to be 0. So that means the tension force is equal to the weight of the block. And the mass is given, so the weight is just mg, and we see that T2 is 98 newtons. Now let us look at the 5 kg mass and draw its free body diagram. And there are actually 3 forces acting on this block. The T1 tension in the first part of the rope, which is directed upward, and then there is the weight of the 5 kg mass vertically downward, and then the tension force, in this case it is also directed vertically downward, because the 10 kg block is pulling the 5 kg block downward. So that is the tension force that is being exerted on the 5 kg block. So the T2. You see the free body diagram in this slide. And now again we apply Newton's second law and sum all the forces. T1 minus T2 minus W1, the weight of the 5 kg mass, equals ma. And so the system is static, so acceleration is 0. So we set this to 0. And then we find an expression for T1. T1 is just equal to T2 plus W1, the weight. And we have already solved for T2 in the last problem. And W1 is just the weight of the 5 kg mass. And if we plug in the numbers, we get 147 Newton. Let us look at another problem. So these are masses on a spring. So now the system is not static. It's the same system as before, but now the system is not static. An upward force of 200 Newton is being applied to the system. And the problem asks us to find what is the acceleration of the system and what is the tension T. So to find the acceleration, because the blocks are connected to each other, we can treat the 2 blocks as a whole system and then apply Newton's second law on the system. In that case, we don't need to consider the tension forces. But we do need to consider the weights of the individual masses, because these are still forces that are acting on the system. So if we sum all the forces, we have F acting upward and the 2 weights W1 and W2 acting downward. So F minus W1 minus W2 is equal to the total mass of the system times the acceleration, because the blocks are moving together. We know the weights because the masses are given, and we know the total mass of the system also. We know the applied force F, so we can find the acceleration A. You can see that A plus G, if I rearrange the expression obtained from Newton's second law, we see that A plus G is equal to F over m1 plus m2. And if we plug in all the numbers, we get 4.3 meter per second square for the acceleration. So the whole system is moving with an acceleration of 4.3 meter per second square. Now let us go to the second part of the problem. What is the tension T? And now let us use the free body diagram of the 10 kg mass. And the 10 kg mass is under just 2 forces. One, its weight acting vertically downward, and the tension force acting vertically upward. And so we can write T minus W2 equals m1 times the acceleration. We have already found the acceleration in the last problem. We know the weight of this block, W2. And then if we plug in all the numbers, we get 141 Newton. All right, so here's a somewhat complicated problem, but you can still use the same principles that you have already learned. So this is a common problem that often you will encounter in homework sets or tutorials or even exams. And it shows 2 blocks connected by a pulley. One block resides on an inclined plane at 30 degrees to the horizontal. The inclined plane is at 30 degrees to the horizontal. The 2 blocks are connected by a rope through a pulley, and the other block is 2 kg in mass, hanging vertically, as seen in the diagram. The problem tells us that we have to deal with kinetic friction also with a coefficient of 0.25. And so the problem asks us to find the direction in which the blocks move. We can look at the two bodies individually, draw their free body diagrams. First, let's look at the 2 kg mass and draw all the forces acting on it. So its weight W1 is acting vertically downward, and we know the weight because we are given the mass. And there is a tension force in the rope that's acting upward. And now let us draw the free body diagram of the 5 kg mass. Its weight is acting vertically downward, W2. We know the magnitude of the weight, the magnitude and direction of the weight. The normal force, however, in this case is perpendicular to the surface. So the weight and the normal force are not acting opposite to each other as in previous problems, right? So there is a tension force pulling the block to the left, and there is a frictional force that opposes the motion of the block. We don't know yet the direction of the frictional force. We just know that it is directed opposite the direction of motion, and the direction of motion is something we have to find out. So these are the two free body diagrams of the problem, and now we can work on the 2 kg mass, find its weight first, and write Newton's second law for the 2 kg mass. Notice the two blocks are moving together, so their acceleration is the same. From Newton's second law, I can write, for the 2 kg mass, I can write this equation, T minus W1 equals M1 times A. A is an unknown, T is an unknown, but we know the rest of the variables. Now let's look at the free body diagram of the 5 kg mass, and we need to assume a coordinates axis that lines up with the slanting surface. That will make the problem easier to solve. And we need to resolve the W2 weight into components along each of the axes, x and y axes. The coordinate system is shown in green in this case by the green dotted arrows. And we can resolve the component of the weight as a horizontal component along the slant, and another component, vertical component perpendicular to the surface of the slanting plane, inclined plane. And because we are given the masses, we can find these components W2x and W2y from the angle. You can see that the weight and the inclined plane forms a right triangle, and one of the angle is given, so we can find the other angles and all the components. Now once we have resolved the perpendicular component of the weight, the component that is perpendicular to the surface of the slant, that component is equal to the normal force, right? Because the block is not moving perpendicular to the inclined plane. So we know the normal component. Once the normal force Fn, if we find W2y, that is equal to the Fn. And then the frictional force, the force of kinetic friction, that is mu times Fn. So we know Fn now. The problem tells us mu k, which is 0.25. So we can find this force also, 10.6 Newton. And so now we can write Newton's second law again, but for the case of an axis that is directed along the inclined plane. So this equation then becomes W2x minus Fk minus T, and this is equals to M2 times A. M2 is the mass of the 5 kg block given in the problem, and A is something we need to find out. T is also an unknown. So, but all the other variables in the problem are now known. So then we see that we have got two equations, one for the 2 kg mass and the other for the 5 kg mass, and we have two unknowns, T and A. So we can eliminate T and find the value of A, and the sign of A will show whether the block is moving to the right or to the left along the inclined plane. We'll leave the solution as an exercise for you. You can try and work this out.